Okay, so the last section gets into the fundamental theorem of calculus and some of the different properties. All right, so this shows a bunch of different stuff. I'm just gonna teach you this part. Okay, so first of all, you can include this under the antiderivative function. Notice what this is saying is the capital F is the antiderivative. All right. And whatever's on the top, we take the top, plug this in, minus the bottom to find the value. And that's really what the investigation is kind of meant to do, is to show you that. But that's truly the fundamental theorem of calculus, is if we're integrating from A to B. Now, what's really important here, people get kind of confused. Antiderivative, the other word for that, the integral. They really have nothing in common, do they? The antiderivative is kind of maybe the in between the derivative and the integral. This sounds like it's the inverse. This doesn't, but it is. These are the same thing. Okay. For a continuous function f of x with an antiderivative capital F of x, when we integrate, that's just the verb for the integral symbol. When we integrate from A to B, we do the capital F of B, top, minus capital F of A, the bottom, to find the value. Okay, so one of the things that I think is kind of helpful, and I really didn't give you a lot of space for this, and I need to adjust my note sheets for next year, is maybe on the top of the fundamental theorem of calculus, make a little graph. We're going to go from A to B and see if this helps a little bit. All right. First of all, we're going to go kind of, I don't know, just make something up. Since the integral represents the area, if the value goes from A to A, basically if I don't go anywhere, there's no area. That's why the integral value would be 0. Second one, if we integrate a constant, k, that means, think of that graphically. If we integrate a constant, isn't this just a rectangle? So we take that k, that constant value, times the distance from A to B. This is really just our length times width. So this is only when k is a constant. This one's important. If we start with B to A, if the only thing we do is switch the order from A to B to B to A or vice versa, they're just opposite values. So if I look over here, if we start and go from A to B, that will be the opposite value. So say this is 7. If I go from A to B, it would be a positive 7. If I go from B to A, it would be a negative 7. When you reverse the order of integration, it just flips the sign. If you have a constant inside times a function, you can just pull that constant outside of the integral and integrate the function itself. All right, this is called the additivity rule. This has got A, B, and C. All right, does it make sense? if we go from A to B and find that area, then we go from B to C and find that area, we really can just don't need to do something twice. We could just go from A to C. So A to B plus B to C equals A to C. We can just condense the process. Now, this only works if the top of this one matches the bottom of that one. And this is your sum and difference. Just like when you do derivatives, you just work your way across, plus or minus. Same thing for antiderivatives. If this is a plus on this side, you're just going to add your antiderivatives. If it's a minus on this side, you're going to subtract them. It's the same thing as derivatives. This is just a proof. All right, so example 4. Remember, how do we calculate the area between? The area between the x-axis and y equals x squared is the integral from 0 to 1, the bottom to the top, of the function x squared dx. So first we're going to find the antiderivative. So take your x squared, add 1, and divide. I'm going to write this like this and carry down my 0 to 1. This is just the notation that is easiest to use. Then we plug in the top number in for x. So 1 to the third divided by 3 minus, plug in the bottom, 0 to the third divided by 3. Well, that's just 1/3 minus 0, which is 1/3. All right. Letter B. Now remember, the area is only if the function is above the x-axis. It has to be greater than or equal to 0. But x squared and the square root of x are both above. So we're going to integrate from 1 to 9 of the square root of x. I'm going to go ahead and just replace the square root of x with a power, x to the 1/2. So when we add 1, that's 3/2, and divide by 3/2. Remember, when you divide by a fraction, you multiply by the reciprocal, and we're going to evaluate that from 1 to 9. All right, so when we plug 9 in, 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. So remember, what is 9 to the 3/2? I'm going to just write this up here. We keep the base of 9 the same. I'm going to take that 1/2 power, convert it back to a square root, and raise that to the third. So the square root of 9 is 3. 3 to the third is 27. And 1 to any power is just 1. So 2/3 times 1 is just 2/3. And then I'm going to just keep my thirds so it's all a common denominator. 2 times 27, that's 54/3 minus 2/3 is 52/3. So one of the things how I'm really kind of picky about that constant, if you're evaluating it from a specific numbers, the constant is just embedded within your evaluating. So, and that's it.